Hello, everyone. My name is Min-Hui. I try to host this webinars, WCRP webinars on the digital Earth. This is a series on the high-resolution land model and land atmosphere coupling. Today, it's our pleasure to have Dr. Hongchen from University of Connecticut that he will present, as you can see from the title, about summertime near-surface temperature biases over the central United States in these convection-permitting simulations. So before that, let me briefly introduce Hongchen. So Hongchen got his PhD from UC Irvine in the Department of Earth System Science, and in 2019. And over there, he worked with Dr. Mike Preacher on the superpolarization model. And then after he got his PhD, he went to the Lawrence Livermore National Lab for a postdoc about 3 years. Then right now he's working in University of Connecticut. And then I knew Hongchen is from other people's introductions about a paper, actually the one he will introduce today, about how to use a kind of a co-resolving model or convection-permitting model to study the land atmosphere interactions. So this is kind of one of the main objective in this webinar series. So with that, I think Hongchen will give a presentation about 25 minutes. And then after that, we can have quite in-depth discussions. And later, if you have any questions, you are welcome to type your questions or raise your hand afterwards. Okay, with that, Hongchen, I will give the time for you, and then please.
All right. First of all, thanks for having me. It's a pleasure to be here. So I'd like to thank my colleagues at Lawrence Livermore National Lab, Pacific Northwestern National Lab, and UK Met Office. Acknowledgement given to the RGMA and ASR programs, as well as the NERSC computing for their computing support. So the title of the presentation, Summertime Near Surface Temperature Areas over the Central US in Convection-Permitting Simulations. So here, let me use the laser here. So in the middle panel, this figure shows the biases of summertime T2M precipitation in CME5 historical simulations. The upper panel shows T2M biases. The lower panel shows the precipitation biases. Here, stipulant means 2/3 of the model agree on the sign. So you see the warm biases here in the CME5 historical simulation. And also over central US during summertime, you have this dry bias of precipitation. Well, in CME6 simulations, on the right panel, upper right, still it has this warm biases of 2-meter air temperature manifested in the data max and the temperature Tmax, and also have this dry bias of precipitation. So it's quite systematic across CME5 and CME6 simulations. What's more, in the short hindcast simulations done by a variety of NWP and climate models in the COSIC project, which I'll describe a bit more in a few slides, also see this widespread central US warm biases of T2M during the summertime. So this systematic pattern really needs better understanding. So that's why we started this project. So there are multiple contributing factors to this issue. From atmospheric perspective, mesoscale convective systems can deliver 30 to 70% of total warm season precipitation over central US. Well, the conventional GCMs are unable to capture these MCS. From land perspective, groundwater, lateral flow, irrigation might also contribute to the issue. Thirdly, misrepresented land atmosphere coupling in climate models might also play a role here. So a few years ago, the project called COSIS was established, cloud above the United States and areas edge of surface, which is a coordinated multi-institutional project using 9 NWP climate models to determine the origin of the summertime T2M bias over central US. In a nutshell, they conclude that the part of the T2M bias comes from radiation errors stemming from misrepresented cloud regimes. For example, missing deep cloud regimes or cloud having two-way relative effects. They found secondary contribution from surface albedo. In my 2018 paper, they also established this theoretical approximation to separate T2M bias in the model from two terms. One is called radiation, the other from evaporative fraction. In John 2018 paper, they delved into the SIMI-5 image simulation. They found similar sources of T2M biases. And given recent progress in convection-permitting simulations for kilometer scale climate models and their capabilities to improve simulations, number one, MCS, number two, surface climates, number three, land atmosphere coupling. So one may surmise that CPMs shall improve the surface climate representation over central US during the summer. So there's a need for a comprehensive study on summertime T2M from the lens of CPMs. The current study really aimed to fill this gap. So we try to answer three questions. Number one, how do biases of summertime T2M CPMs compare to those in causal resolution models? And do they arise from similar reasons? Number two, what's the relationship of T2M to precipitation and MCS in particular? And through what physical processes does the surface force the atmosphere or vice versa? Number three, how can CPMs from engineering perspective be changed to reduce the biases in T2M and MCS? So in our study, we looked into 10 convection-permitting model simulations in total. So let's work through those one after another here. I started with the name tag. The first simulation called Worf-Morrison using Worf version 3.6.1, and the other called Worf-Thompson. The only difference from Worf-Morrison is microphysics changed from Morrison to Thompson scheme. The third is Worf-PBL land radiation using slightly earlier updated version of the Worf changes in PBL scheme, land surface model, and radiation scheme. The rest of the simulation come from NEM simulations. The RE2 mid-phase, regional atmosphere version 2, mid-physics configuration, mid-latitude physics configuration. The RE2 trough phase is NEM regional atmosphere version 2, tropical physics configuration. The RE3 is default version 3 of regional atmosphere NEM. The RE3 plus trans, meaning based on the default RE3 simulation, there is additional enhancement of cloud transpiration. The RE3 plus trans plus infill is based on the RE3 plus trans, but there is additional enhancement in circuit infiltration. The RE3 plus trans plus infill plus micro is based on the RE3 plus trans plus infill, but cloud microphysics changed to one moment scheme. The last one is RE3 plus trans plus infill plus micro plus macro, meaning based on the previous RE3 plus trans plus infill plus micro simulations, we are changing from microphysics to prognostic treatments. So all of the simulation have horizontal resolution at 4 kilometers. For the Worf vertical layer, 65. For the NEM model, it's 70 vertical layers. And within our simulation, we have 5 pairs of sensitivity tests where the model changes can be detected, can be attributed to a single parameterization change. For example, RE3 versus RE3 plus trans, we know the model behavior difference is due to cloud transpiration enhancements. The RE3 plus trans plus versus RE3 plus trans plus infill, we know the model behavior changes can be attributed to surface infiltration enhancements. Furthermore, with Morrison versus with Thompson, we know the model behavior changes can be attributed to cloud microphysics. So we have these 10 sets of high resolution Worf and NEM simulation in different configurations with the sensitivity test on transpiration, filtration, cloud physics. The simulation domain covers contiguous US, 2850 north, 12075 west. The simulation period is from May to August of 2011, given the computational cost. The MCS tracking was done by the flex tracker algorithm, which is well documented in the 2018-2019 paper. And we analyzed these 10 CPM simulations alongside with 9 causal resolution process model simulations. So the MCS tracking, first, the flight tracking algorithm will first describes a cold cloud system or CCS using a geostationary satellite infrared brightness temperature TB and low-level radar reflectivity. Then it discerns the MCS by radar-defined convective and precipitation features. The criteria for MCS, number one, the CCS, covering at least 6 times 10 to the 4th kilometer square area, and a continuous precipitation feature and precipitation rate greater than 1 millimeter per hour, with at least 100 kilometer length in its major axis. Number two, a convective feature with at least 45 dBz radar reflectivity at any vertical level. Number three, just previous two criteria has to be satisfied for more than 6 hours. So this panel is our results, basically show the T2M biases in CPMs over summer of 2011. The upper left panel is show Worf-Morrison simulation. Upper middle, Worf-Thompson, this is Worf the land radiation simulation. The second row, RE2 main phase simulation, the RE2 top phase simulation. This is default RE3. This is RE3 plus trans, RE3 plus trans plus infill, RE3 plus trans plus infill plus micro. This is the RE3 with full flash sensitivity tests. And lower middle panel is the multimodal mean CPM simulations. The lower right panel here is the multimodal mean of closer resolution cosmic models. And we also average over the central US black box triangle there. The colored markers are representing different CPM simulations. Here, the second row, second column, the gray markers are representing color resolution cosmic models. Here, the observational benchmark is from NOAA QLCLD quality control data. So first and foremost, we still find that CPMs still suffer from T2M biases for central US during summertime, magnitude of which varies by model. The RE2 mid-phase and RE2 top phase have the largest form biases. The RE3 plus runs, by enhancing clone transpiration, surface filtration, and drastically reduces the T2M biases by 1.58 Kelvin and 0.59 Kelvin respectively. This panel, same layout as previous figure, but show the bias of precipitation. Here the benchmark comes from NCAR stage 4 precipitation data. So CPMs still suffer from precipitation dry bias over central US, with maximum center mean in Nebraska and Kansas. The RE2 mid-phase, RE2 top phase have the largest dry bias, consistent with the strong T2M bias you see previously. By comparing RE3 default versus RE3 plus trans, we know that enhancing vegetation transpiration can increase precipitation by 0.74 millimeter per day over central US. And by changing the cloud microphysics from Morrison to Thompson scheme, the Worf simulation have decreased precipitation by 0.67 millimeter per day. So changing cloud microphysics definitely can have an noticeable impact on precipitation over central US during summertime here. So this panel shows the evapotranspiration diffraction bias in CPMs here. The RE2 mid-phase, RE2 top phase shows severe underestimates of EF and consistent with the largest T2M biases. And without interference in transpiration infiltration, the RE3 default underestimates EF over the central US. And by enhancing clump transpiration, we found that has largest impact on the EF, which is increased by 0.16. Here, observational benchmark comes from the FluxNet. So in my 2018 paper, they have this analytical derivation on how to decompose the T2M bias in the model into 2 terms eventually. The first term is due to radiation, consists of short wave and long wave components. The second can be associated with the evapotranspiration diffraction bias term. So we use the same analytical framework as a Meyer 2018 paper and applied to the CPM simulations. So here on the lower left panel, we applied the analytical framework over central US region. The x-axis showing the radiation contribution, the y-axis showing the evapotranspiration diffraction contribution. The middle panel applied at SGP site, Southern Great Plain, where the high quality observational data are readily available, sort of independent validation and the calibration. And the right panel shows the correspondence between EF biases versus T2M biases across different CPMs. So this analytical framework suggests that T2M bias in CPMs could be attributed to errors in surface EF and radiation terms. And interestingly, if you focus on the intermodal spread on the y-axis, that's EF contribution, that's much larger than the intermodal variability over the x-axis, that's radiation contribution. So again, underlines the importance of EF. And we also found strong correspondence between EF bias and T2M bias over some during summertime over some of the US across those CPMs. So in the next section, we'll delve into the relationship between T2M and precipitation MCS, and also investigate the interaction between land and atmosphere, these two interaction theory. So this panel on the left shows the MCS rainfall observations, that's panel A, and different CPM, that's the rest of the panels during summertime 2011. This table shows the summary over central US in terms of observation and CPMs, the MCS frequency, MCS rainfall, and the MCS rainfall fraction. Here, the fraction simply means the contribution of MCS rainfall to total precipitation. So over central US, almost all models underestimate summertime rainfall from MCS, and most CPMs have a smaller value than the observation of 1.7 millimeter per day. We found most severe underestimate occurred in the RE2 mid-phase and RE2 12-phase simulations. In the RE3 plus runs, enhancing vegetation transpiration and surface infiltration improved the MCS statistics across the board, including the rainfall frequency and fraction. So here in the Wolf-Thompson simulation, MCS rainfall and its contribution to total precipitation are underestimated despite over the high MCS frequency, suggesting that MCS intensity is biased low here. So we also looked into the propagating features of MCS. So this panel homologue diagram, MCS precipitation. The first row, second row is non-MCS precipitation. The third row is total precipitation. The first column is showing observation, then the Wolf-Morrison, Wolf-Thompson, Wolf-PBL land radiation, and the rest of the CPM simulation, different columns. So the nocturnal features of MCS are better captured in some models than others. And also in observation, local time around 6 p.m., longitude 103 west, the MCS initiated and then propagate eastward. This feature is absent or weak in most of the models and only captured by the Wolf-Morrison simulation. And we'll compare the third and second column, that's Wolf-Thompson versus Morrison. We know by changing the cloud microphysics to Thompson simulation, nocturnal MCS signal is dampened significantly. Changing land physiology and hydraulics also improve the propagating features of MCS in those RS3 plus run simulations. So this slide, we're trying to distill the impact of the atmosphere on land by looking into different terms of surface water budget. Upper left panel, accumulated precipitation. Upper right is accumulated ET evapotranspiration. Soil moisture, middle left. Surface runoff, accumulated values, lower middle right. Lower left is a T2M bias, and accumulated MCS precipitation shown on the lower right. So here, upper left panel, the black solid curve is from observation, and the rest different colored curves are from CPM simulations. So some CPMs show lower accumulated ET than others, primarily R2 mid-phase and trough-phase simulations. Accumulated surface runoff is quite large in the R2 simulations, but small in R3 series with plus infiltration treatment, which is reassuring because that's by design. And also there's intermodal spread of accumulated precipitation and MCS precipitation by the end of May. And such spread becomes larger and is driven by MCS precipitation. You can see panel F here. Changes in soil moisture is consistent with a trend accumulated precipitation, and differences in soil moisture between the CPMs become relatively stable around June 7th and persisted through the rest of the summer. Well, this panel shows the correspondence between May precipitation bias and summertime T2M bias across CPMs, upper left panel. Panel B, upper right, is showing summertime EF bias versus May precipitation bias. correspondence between May precipitation and soil moisture change, lower left panel, summertime soil moisture versus summertime EF correspondence, lower right panel. We found strong correspondence between pre-summer mean precipitation bias and summer mean T2M EF bias as shown in panel A and B. May precipitation highly correlate with soil moisture change in panel C with Pearson's R.89 with minuscule p-value. And also the summertime soil moisture affects EF manifested in corresponding C in panel D here. And overall, we conclude that together with the time series plot, we think the pre-summer precipitation can impact the subsequent summertime T2M and EF by altering soil moisture. Well, this panel tried to investigate the impact of land on the atmosphere and in terms of shallow convection. The correspondence across CPMs shown on the panel A is T2M bias versus humidity. The T2M bias versus lifting condensation level, panel B. Panel C is T2M bias corresponding to boundary layer height. Panel D is T2M bias versus lifting condensation level deficit. Here, LCL deficit is defined as PBL height minus lifting condensation level. It's typically a negative value. Closer to 0 means it's more likelihood of cloud formation. So if a model has larger T2M biases, it has more sensible heat flux and less latent heat flux. There's lower specific humidity and higher boundary layer height and lifting condensation level. And for a unit increase of T2M bias, LCL increases faster than the PBLH. There's more negative LCL deficit, and which is the less favorable condition for the shallow convection and cloud formation. Such condition can be alleviated by enhancing transpiration and infiltration in the RS3 plus runs. You focus on the magenta versus pink and versus purple triangles. And similar effects, irrigation on PBL condition can be found in the Cheng et al. 2020 paper. Well, this panel, we're trying to investigate the impact on from land to the atmosphere in terms of deep convection. So the left panel here showing the summertime T2M biases is corresponding to latent static energy. And the second column shows the corresponding between T2M biases versus lowest model layer moist static energy. The third column, lowest level MSC versus Cape, convective available potential energy. And the rightmost column is showing the corresponding between Cape versus precipitation. So we found there's a strong anti-correlation between T2M bias and near surface MSC during local afternoon. And models with larger T2M biases show smaller MSC driven by the moisture components. And the smaller surface MSC contributes to a smaller Cape, meaning there's less deep convection and precipitation. Models with smaller T2M biases have a closer to 0 LCL deficit, and there's higher likelihood of shallow convection, which moistens the lower troposphere and contributes to a larger Cape. So to summarize, to answer our question 1, contrary to our original hypothesis, we find T2M warm biases are quite common in CPMs, and spatial extent and magnitude are similar to causal resolution models in the CAUSES project. CPMs generally underestimate precipitation, including MCS rainfall, and they substantially underestimate evaporative fraction. Another commonality between CPM and CAUSES models is that the intermodal variability of evaporative fraction contribution is much larger than that from the surface radiation contribution, underlying the importance of EF. We found compelling evidence that T2M warm biases will degrade the simulation of total and MCS precipitation in a model. Models with T2M warm biases have too low ET and too dry daytime boundary layer. Furthermore, the daytime boundary layer is too high due to overestimated sensible heat flux, which further aggravates the boundary layer dryness due to intermittent drying effect. The boundary layer dryness results in the LCL that is too high above the boundary layer, making it difficult to form shallow convective clouds, which can transition into deep convection. The dry boundary layer has a low MSE and reduced Cape, and with lower afternoon Cape, the potential to form precipitation MCS reduced. So to answer our question 3, how can CPMs be changed to reduce their bias in T2M MCS? We think modelers should focus on surface ET and EF. In any model they find a summertime warm bias over central US. And from our modeling pairs of sensitivity tests, it seems like changing line component can be more impactful than changing atmospheric components in driving the T2M changes. The caveat here is the smaller impact atmospheric process on T2M bias may partially just be due to the moderate nature of model changes. So final remark, increasing model resolution is not a panacea. To fully reap the rewards of CPM in simulating convection, MCS, and precipitation, a realistic representation of the land surface climate is essential, and which is a reminder of the coupled nature of summertime climate over central US with its strong land atmosphere interactions. So with that, I'll stop here and start to take questions. Yeah, thank you. Thanks for your attention.
Well, Hongchen, thanks very much for this comprehensive presentation, and then try to address the three major questions that there's been long-term questions about this dry and warm bias over there. Very nice, thank you. Yeah. For the audience, you're welcome to raise your hand and or type your questions in the chat box. And I think there is one question from the chat box. Hongchen, can you see it? He's asking about which season you are talking about.
Yeah, I'll repeat the question first and then try to answer the questions. The question here I see is the biases during 1979 to 2005 is for which season, summer or winter? So here is, I think the reference is, yeah, the bias here we discussed are summer only. So boreal summer to July, August.
Yeah, so this is previous those GCM simulations, those biases are also talking about during the summer, right?
Right.
Okay. And okay, there's another question about, yeah, do you want me to read it or you can see it?
Yeah, I can see it. So why does accumulated ET appear more linear compared to other variables from May to September? So why does accumulated ET appear more linear compared to other variables from May to? I don't think I fully understand the question, but I think it relates to the yeah, the question seems to be asking why accumulated ET. Okay, I have a figure here. Oh, I see what's the question concerns. Yeah, that's a very good question. That's a very good observation. Yeah, I do see that the accumulated ET panel seems to be more linear than other curves. You see like more jig-jag.
Can you show the figure? Can you share the screen?
Sure.
I mean,
yes. Let's So I think that question asks why accumulated ET seem to be more linear than other curves we analyzed here. Yeah, that's a very good question. I hope I knew the answer. But yeah, I do feel the surface runoff is has its finer temporal variabilities, but accumulated ET seems to be smoother. Is it related to large scale versus small scale processes? Or yeah, that's a good observation. I don't think I have a perfect answer for that. Yeah.
Yeah. So maybe try to decompose it, because those three terms that from total ET,
right.
maybe
yeah, the canopy
can see something. Yeah.
Yeah, that's a good suggestion. Yeah, thank you, Dr. Lau. Yeah, decomposing those into transpiration, bare ground, and canopy evaporation would be a good way to go.
To see how it goes. Yeah. Okay, that's cool. And Jimmy There's another question.
Right. So this question is Barrelage, as you noted, found that groundwater recharge was an important process in keeping moisture fluxes up. Yes, that's a very good reminder that the Barrelage, I believe they did groundwater process in the WRF model, and they find the warm biases can be alleviated quite significantly. I think that's a very important reminder. Yeah, thank you. Yeah.
Okay, cool. And there's another question from
Yes.
Cheng.
Yeah, Dr. Fu. Yeah, Dr. Fu asked the Morrison versus Thompson simulation. When we change it to cloud microphysics, it shows large differences in simulated MCS. Do we have any insight on this difference? The short answer is I don't know. I think Zhe Feng, who provided us the warp simulations and changed it to cloud microphysics, might have more insight on this question. But that's a very good observation. Yeah, changing cloud microphysics changes the simulation of MCS. That's our result, but I don't have the scratch in my head. I don't have satisfactory answers of why that happened this way.
Okay.
Yeah.
And Mega is a follow work. Yeah.
So Dr. Fowler, Megan, great talk, Hongchen, you the improvements in T2M bias in the higher transpiration are really. So the question is, the improvements in T2M bias in the higher transpiration are really compelling. So I'm wondering if you've looked into biases in the land models used. Is total ET biased low, or is it that soil moisture is too low, or land cover type not accurately captured in the land models? Oh, those are very good questions. So, yeah, is total ET bias low? The answer is yes. As Dr. Low suggested earlier, a decomposition of total ET into different components might be very useful to just trace back to which component is playing a dominant role here, or is this soil moisture too low? Or yeah, we also find overly low soil moisture in the CPM simulation over central US during summertime. So that's also yes, the soil moisture is too low. Land cover type. So I don't think this paper discussed too much about land cover type, but I do recognize the importance of different tiles. Like, is it maize, or is it other types of crops, or yeah, that could be very important too. Yeah. Thank you, Megan, for those questions and potential advice.
Okay. So, and may I for this question, may I add one more? Like maybe last year or the year before, there are like two papers talking about the irrigation's impact on these dry biases in the central US. So I just wonder, those lenses models has considered irrigation practice in those simulations you have done?
I don't think irrigation process is incorporated in our warp simulations. So that's an answer.
Okay.
Yeah.
I see. Okay. Cool. Thank you. And we have Kate here. Can you see the question?
Right. So how did you modify the transpiration? So the transpiration here sensitivity test is done by one of our collaborator, Quentin, and some experts at the Met Office. So if memory serves, there's a parameter. I think that's surface infiltration, right? So there's a parameter to control surface infiltration. So they increase the parameter to do the infiltration enhancement. But for the vegetation, is it still model conductance or modified or other type of process? I can't recall precisely, but I can reach out to Quentin to reach out to Kate if that's a very engineering engineering trick you'd like to do as well. Yeah, stormwater conduction might be the way I could think directly you can interfere with.
Yeah, I think Quentin will respond. The
Yeah.
temperature threshold for photosynthesis and the BPD
right.
as well.
Yeah, I think we have that paper. We have that discussion in our that supplemental material or the main text. I sort of forgot, but yeah, Quentin answered. We changed the temperature threshold for photosynthesis and vapor deficit limit for shutting off transpiration. Right. Oh, thank you, Quentin. Yeah. In the model, transpiration stops as soon as particular temperature, right? Vapor deficit limit. Yeah, that's right. That's came to mind. Yeah, there is a threshold of temperature and vapor deficit reach limit, which we modified for each plant functional type PFT. Oh, thank you, Quentin.
Okay.
Yeah.
Okay, so I wonder is this modification for changing the temperature threshold is similar to change the resistance directly, or is different?
Yeah, that's a follow-up question.
Yeah, maybe Quentin can respond or. All right.
Yeah, similar, changing the resistance.
Okay, cool. Thank you. Okay, we have, there's a Q&A. Okay, Max, sorry. I just saw this and I think you have posted your question on the chat box already. Okay, cool. All right. Any questions from the audience? I actually have one more, like in the beginning when you show those biases from the GCMs, and later on those biases are for the CPMs. Just wonder, of course, the resolution are quite different between GCM and CPM, but the overall the shape of those biases are quite somehow different. I mean, at least from my take a quick look of your presentation. So I just wonder, do you have any comments on those different shapes of those biases? It's not like confined within the central US. Sometimes that is kind of a little bit tilted or.
Right. I agree with your assessment, Dr. Low. There's intermodal variability on that. So one physical process I could think of is if a model misrepresents where the MCS initiated, where it dissipates, that might have a huge impact.
Okay.
So MCS precipitation, the pre-summer precipitation can impact summertime soil moisture and summertime latency interactions. If the MCS is mislocated in the model, the T2M bias might be just pop up in different places. That's one I could think of.
Okay, so this could be from the atmosphere model biases.
Yeah, it could be from land as well. We just can know the precise answer here.
Yeah, sure.
So here is another question. As you mentioned, the land surface scheme used in models is very important. Did you examine how well the land surface fluxes partition net radiation into latent and sensible heat? So we have evaluated the spatial patterns, how surface latent heat flux and sensible heat flux are represented in the model over Central US comparing to the FluxNet MTE by John et al. Paper. The Born ratio is another more direct comparison. I think that's more related to your question. Also at SDP side, we have RMBE data which is more high quality, and we compared that to the different CPM simulations. So I think that's one we did in our paper.
Mm.
Yeah. Oh, so yeah, Quentin maybe so Quentin put a comment related to Dr. Chang Fu's question. We noted a paper in 2013 that the Morrison scheme has much more small ice aloft, while Thompson has more snow, which sediments quite quickly. This will impact envelope sizes on which these tracking algorithms rely. And also, there's a link posted in the comment. That's a link to the paper.
Okay.
Oh, thank you, Quentin. Yeah, thank you.
Okay, so this is talking about the impact microphases on the MCS. Okay.
Right, that's very very interesting question. Yeah, thank you, Quentin, for posting that paper here.
Mm-hmm. So may I ask the follow question about Bijana Music's question about how well is the net radiation partition to latent heat sensibility? So just curious whether you have done some assessment for the GCN and also CPN, how those partition are different. When especially if there's some observations when you compare, do those CPM models perform better for the partitioning?
I think that might be one interesting research direction. So in my previous work, we do find that cloud superparameterization was another way to achieve a convection-permitting simulation.
Okay.
Across different model versions and also across different simulation types, cloud warming simulation types, climate warming simulation types, they over land, not ocean, over land, there's a enhancement, systematic impact of the enhancement due to cloud superparameterization. I haven't looked into the 4-kilometer simulation in those 10 CPM simulations I examined here, but I do think that's a very interesting value to pursue Born ratio thing.
I see.
Yeah.
Okay. Thank you.
Well,
I guess well, it's a very fruitful discussions.
Yeah, I think it too.
And all right, so I think thanks everyone. Those questions I think make this webinar more meaningful, and I think thanks Hongchen's time on these presentations, and then share with us your results from the papers, and also some perspective on this high resolution land model and land atmosphere coupling issues. Thank you very much.
Oh, my honor to be here. Yeah, thank you. Yeah, thank you everyone for the comments and your time being here.
And I would also like to advertise our next webinar will be in 2 months, and will be August 8th, the same time, and then will given by Dr. Junhong Lee from MPI. Okay, and we'll also talk about this high resolution cloud resolving models, especially focus on the land atmosphere interactions. So all of you are welcome to join our next webinar. Well, with that, I would like to thank you everyone again, especially Hongchen. Thank you.
Yeah, thank you everyone. Take care.
See you.
Goodbye.
Okay, see you. Bye-bye.
Yeah, thank you. Goodbye.